Yeah, Mr. Ajay, can you share the screen, please?
Yeah, thank you. I'll be reading the ISHRAE Code of Ethics. In this ISHRAE meeting, we will act with care, dignity, and consideration, upholding all values of trust, teamwork, meritocracy, and justice. We shall not exploit the society's forum for any commercial or personal gains and shall avoid all real or perceived conflicts of interest. And that our thoughts, words, and actions shall not besmirch the image and standing of ISHRAE. And I say, I do.
I do.
Morning, everyone, and thank you for taking time to join the training session. I think it is so important that we continuously take time to learn. My name is Ajit Abraham. I am the president of the ISHRAE UAE subchapter. For all those who are members, you would know me. For all those who are not members, it's just a general introduction as to the ISHRAE UAE subchapter. Is in the UAE, it's our third year, but uh, for ISHRAE from India level, we've been I mean, we are a body with over 25,000 people, and it's a platform where we network, we connect, we learn, and at the same time, if you are working in the engineering side, or if you are even connected to the engineering industry, or even if you're a student who is pursuing the field of engineering, I would always advise and recommend that you be a part of the ISHRAE forum, a great platform where you can learn, where you can connect, and at the same time also grow in knowledge. The ISHRAE UAE subchapter, though we are in our third year, there are a lot of activities that take place. Training being one of our core focus, imparting of knowledge is our key focus, and we will be having training sessions, physical or online for sure, every month. So I would always look forward to seeing more participation and more engagement of individuals who are members. And if you're not a member, I would really request you to be a member, because you will get a lot of advantages of being connected. We also have technical conferences, women events, sporting events. So our engagement is at different levels, at different category, and also even students, they also have an opportunity to engage at their level. I'm not going to take much time, because I know we have Ajey Joshi who's here to give a wonderful presentation. I would hand it over back to our technical chair, Harshal, who will do a brief introduction of Ajay, and then the floor is open. Please do take time to ask questions, to connect, and at the same time, I hope you will make the best use of it. We have a nice time, good learning. Thank you, Harshal. All the best.
Thank you, Mr. Ajit. I really appreciate your time and joining us today. Coming to Mr. Ajay, if you can be on the screen for us. Yeah,
I hope you can see me and hear me.
yeah. Now we can see.
Okay.
Let me introduce Mr. Ajay Joshi. Mr. Ajay Joshi is almost experienced with 3 decades of his consulting experiences. He has worked for big companies, big consulting firms like Tata Consultancy. He has worked for Spectral Services Consultancy, Gruene Designs, and last 18 to 19 years, he has been associated with AECOM, and right now he's working as a technical director. So looking at his 29, 30 years of experience, I'm sure we all can start expecting what we are going to get today. So we are really lucky, Mr. Ajay. Also, I would like to mention he has got his expertise, not just as a consultant in general projects, but mission critical facilities, energy and building, as well as the healthcare facilities, which is a very niche market, you know. So these expertise are very rare among the consultants also. So we are really lucky to have you. And he also has 100 plus mission critical projects globally under his belt. So I'm sure there is no question that he cannot answer probably. And Mr. Ajay, thank you. Thank you so much for accepting our request to take this training for us though you're in India, but you have really extended your hands and support to UAE subchapter of ISHRAE. So we really thank you, and I hand over the floor to you. Please, anything that I have missed, introduce yourself more, and you can start with the training.
No,
Uh, and for all the participants, sorry, last note, we will post intermittently one file, which is a Google file, where you just go put your details so that we can arrange certificates for you, training participation certificates. So we will be posting that link on and off every half an hour probably as the presentation is on in the chat box. Thank you. Thank you, Mr. Ajay. Please continue.
thanks, Arshil. I'm Ajey Joshi, working as technical director at AECOM. As you said, 29, 30 years of experience, and hopefully this will be a good session. So this session is on chill water systems. I will not be covering, usual aspects, which all of us know, like pipe sizing, friction factors, those kind of things, you in fact know better than me. So what I would be trying to do is few fundamental aspects, which will kind of transpire you to think from application point of view. Um, I thought, I would collect such points and kind of, present in front of you so that, as and when such applications come, you can kind of apply that theory and use it for say designing a good chill water system. So with that I would start. Let me know once my screen is visible.
Yeah, it is visible, Mr. Ajay now.
Okay, so we just spoke about ISHRAE code of ethics, very critical, so I won't spend time on this. Let us go to our. Can you see the slides moving?
No, it's not moving,
No,
Ajay.
it did not move.
Okay.
Can you just disconnect and just restart it again? Maybe it will work. Yeah, just reshare it again.
No.
It's not moving yet.
Are you able to see now?
Yeah.
Yes, sir.
I don't know, but for some reason it is not moving. So, okay, I will let me put it on PPT mode. Okay, anyway, so we'll start. So this is about large chill water systems. So even though the title is for large chill water system, the fundamentals, the aspects are actually applicable equally for a medium sized or even small chill water systems. Uh, Now, in any chill water system, maybe big or small, if you kind of try to see which are the basic components, the basic components of any chill water system, as we all know. Yeah. You can see my cursor, right?
Yes, sir, we can see.
Yeah. So basic components, 4 5 components of chill, any chill water system, or for that matter, any hot water system, are basically load. It could be a cooling load or a heating load, a source. It could be a heat pump, a boiler, or a chiller. There will be one expansion chamber or expansion tank, open or close, so which allows for the expansion and contraction of water. There'll be pump and a distribution system, right? So these are the basic components which you will see in any chill water system. So, today's intent is to see critical applications of few of these. Of course, we are not going to talk about heat load calculations, etc., etc. That's a different thing. But about other important equipments and systems in the chill water system, we will try to go through each of them. I hope you can see the next slide.
Yes, sir, it's moving now.
Okay. Now, chill water system, we all know, we call it as closed water system, correct? A chill water system is a closed water system. There are few open systems also, usually for industrial plants where there is a hot well, cold well, but I'm not talking about that for today. I'm talking about closed chill water systems. Now, what do we mean by closed water systems? Now, if you really see definition of closed water system as per ISHRAE, I will read it. A closed water system is defined as system where no more than one point of interface with compressible gas or surface. So this is a definition. Now let us see what it means. If you talk about chill water systems, maybe 20, 30, 40 years back, they used to have open expansion tank on the terrace, correct? It used to be a small 1,000 liter or 2,000 liter tank, mainly plastic syntax. So is that also a closed water, closed chill water system? Yes, because it has only one point of interface with surface, which is atmosphere. There is no other part in the system, which is open to the atmosphere in those chill water systems. So those chill water systems with open expansion tank on the terrace are also called as closed water systems. Nowadays, obviously, we have these closed expansion tanks and all that. So there also, if you see, there is only one interface with the bladder and the inert gas, correct? There are no two interfaces. Is this definition clear? That no more than one interface with compressible gas or surface or atmosphere. So that way, all chill water systems which we talk about are closed water systems. What are the open systems? The open systems is the example is cooling tower water system. Now these systems, as per ISHRAE definition, have more than one interfaces. Now, if you imagine in cooling tower circuit or cooling tower system, which are the two surfaces which are open? One where the nozzle comes from the top, there it actually gets exposed to the atmosphere, and second surface is in the basin, where basin water is exposed to atmosphere. So there are more than one points which are actually open to atmosphere. So that's how, by definition, cooling tower systems are open. Is this correct? I mean, is this clear to all? What is the basic difference between open and closed?
Yes, sir.
So closed water system has only one interface, whereas open systems will have more than one. Now that transfers few theories. You can also deduce that closed systems do not create system flow by elevation difference. Imagine a chill water system of 30, 40, 50 storied commercial building. And if you switch off the pump, there is no way that there is a flow, correct? The flow will be established only when the pump runs. So even though we are talking about 200, 300 meter tall chill water structure, unless the pump runs, there is no way that the water will flow. So in closed water systems, flow is not created by elevation difference. A few of the differences in closed and open system. In closed system, the flow is not motivated by static head difference, as we saw. If the pump is running, then only the flow will get established. However, in open systems, the flow is motivated by static head difference. The difference is if you switch off the pump of a cooling water system, few of the water in upper headers can get emptied, even if your pump is not running, which means the flow can be and gets motivated by static head difference. Another difference is in closed water systems, pump is really not required to provide any static lift. I mean, you can talk about 200 meter tall, 300 meter tall. Pump is really not bothered. It is not required to provide any static lift. What is needs to be only do is to respond to only frictional drops. Whereas in open systems, obviously you are required to provide a static lift. In cooling tower circuit, the static lift is nothing but the height of the cooling tower, right? Because that's two open surfaces through which the water is required to be lifted. So in open systems, you need to consider the static lift. In closed systems, the entire piping is always full with water. In open systems, portion of piping can get emptied upon shutting down the pumps. As I was speaking in the first point, that in cooling tower circuit, if you switch off the pump, some of the water in higher elevation can get emptied into the cooling tower, which is not the case in closed water systems. The entire water is always full, even though the pump is running or not running. That's why if you see, I don't know how many of you you use piping charts nowadays. Obviously nowadays there are softwares, but earlier in my time, 20, 30 years back, we used to use those charts. So there has to be two separate charts for open systems and closed system. So how many of you have used those charts to do the piping? Those will understand that there are two different charts, and the reason is these two systems don't behave in a similar fashion. Little bit about temperatures. When we talk about chill water systems, uh, usually there is very narrow band in commercial buildings, but here we are going to talk about variety of applications. So the minimum temperature which we could kind of see in the industry for plain chill water, I'm not talking about brines, clean or pure chill water, you could see minimum of around 2 to 2.2 degrees centigrade. That's the minimum thing which you can see in the industry. Now these are special applications for DM chill water for probably nuclear power plants, etc., etc. There you cannot use brine. So this is the minimum temperature which you can see, 2 to 2.2 degrees centigrade. And on the higher side, for data centers, obviously, you all might be knowing that this data centers nowadays operate very, very warm. So they require chill water of 20 plus, 22, 24, even 25, even 27. So that's the upper range of chill waters. And obviously for if less than that temperatures are required in sub-zero range, obviously we use brines. This is one expression which I thought I would tell with you. I'm not sure how much important it is for nowadays, because this was there in ISHRAE systems and fundamentals probably 10 years back. When there was no coil selection softwares available, very ubiquitously, engineers like us, used to decide the required chill water temperature on, desired room conditions by this empirical formula. This was TW was coil entering water temperature, TW. TAD was apparatus dew point or coil surface temperature anticipated, and wet bulb was coil leaving, air wet bulb temperature. So this how tentatively we used to design chill water temperatures for given application. Now obviously there is no much use of this formula, because nowadays we all have sophisticated coil selection softwares where really you don't have to go in any empirical way. So this is, I think Arjun Guru has raised the hand.
Yes, sir. I have a doubt on this. I'm audible?
Yeah, we can hear you.
Yes. So this formula holds good for even DX systems like package units or the one which operates on the refrigeration circuit, not on the chilled water circuit. Say example, coil entering temperature. We are talking on the water temperature, but something like same applies for the entering temperature of the refrigerant.
Yeah, I mean, it could be applicable for that. So for long years we are not used, but I thought, this is like a, historical example. So any one of you, is interested, you can use it. It is applicable for hot water as well as, your chill water or, single phase refrigerant. I am not sure if it is applicable for two phase refrigerants, like, your azeotrops, etc., etc. But for sure it would be applicable for a simple gas like R22, or alike.
So we can use it for this formula.
But you may not have to use it now, because why should you use, if you have sophisticated, coil selection softwares, where to get into approximations.
Okay.
This
And
was
one more.
probably 20 years back.
Okay, okay, done. And regarding to the data center cooling systems, chill water temperature of
Mhm.
22 to 24 and beyond, you
Mm.
mentioned, because the
Yeah.
data center right now we are looking at the data center is around like 24 degrees. Suppose, say, example, the temperature has to maintain with 50% RH
Mm.
values or 50 to 60%
Mm.
RH values. Uh, when I want to maintain 24 or 22, but of course my chill water temperature should be around 7 degree or 9 degree, 10 degree. If I maintain 22 degree as a temperature, my data center temperature will go to 30 degree.
Correct, correct. So data centers nowadays operate at even 30, 35 degrees centigrade air temperature inside. Okay. So especially this AIML data centers, they even operate at much higher temperatures than this.
Sir, in that case, sorry, if that case, why won't we consider free cooling?
Yeah, it is considered. So in fact, most of the data centers are,
Hmm.
as they, operate at, very high temperature, uh, 80 to 85% of their time in a year is usually on a free cooling.
Hmm.
There would be,
Okay.
few hours in a year where obviously,
Hmm.
you would like to trim it. So this is actually also known as a trim cooling.
Okay.
So the chiller system, usage is not obviously, throughout the year. It is in a trimming mode.
Okay. Fine. Thank you.
In fact, there could be few applications where, in fact, you may not require a chiller. You can actually cool the water by cooling tower water also.
Hmm. Okay.
If there is
Okay.
dry area.
Okay.
So yeah, that is also possible.
Okay. Okay. Thank you. Okay.
Um, Now, one of the issues which we always see at site is air entrapped into the water or chill water system. Now, why first of all air is bad into the chill water system? Because air is 20-25% oxygen, and when we talk about oxygen, it has a oxidation potential. So if there is too much of oxygen in the system, obviously it is going to corrode your metal surfaces. That's the reason why you really don't want air into the system. Now, fundamentally, how air behaves in chill water system. Now, there is something known as this, solubility of air into the water. So if the solubility is high, obviously the water has higher potential to get air and get it dissolved and carry that air throughout the system. So the solubility of air in water is addressed by a expression which is over here. X is basically, if you call it, solubility of water, it is percentage by volume. It is equal to P upon H. Now, P is basically absolute pressure at that point, and H is Henry's constant. So, a simple observation of this equation would tell you that solubility of water is more or is directly proportional to the absolute pressure, right? So, absolute pressure in the system is maximum at what point? Obviously, at the lowest point. Correct. If it is a commercial building or a hotel, uh, if the plant is in the basement, obviously the absolute pressure. So absolute pressure is basically operating pressure plus your atmospheric pressure. So pressure will be maximum at the lowest point. So at the lowest point, the solubility of air will be maximum. What it means is if the air is is actually soluble in water, you may not be able to remove it. You can remove the air which is only separated out from water. So that's the reason why if you try to separate the air from basement, you would not able to do that very efficiently, correct? Because at that location the pressure is maximum, hence solubility of air is maximum, hence you can't remove the air. So usually, if you see the air removing say devices are at the topmost point. Again, the basis of that is this equation that at the topmost point the pressure is less, solubility is less, so more air is actually available for you to bring out of the system. So this equation gives how much at what elevation what opportunity you have to remove the air. Now the Henry's constant, even if we call it as a constant, it's not really a constant at variety of temperature. It is constant at a given temperature. Let's say you talk about a chill water system at 8 degree, 10 degree centigrade. If you talk about only one temperature, yes, the Henry's constant is constant. But if you change the temperature, the Henry's constant also changes in an inverted hyperbolic way, right? So this is the graph from ISHRAE about temperature and Henry's constant. So for a given temperature, it's constant. So you can apply this equation for a fixed temperature and can say that the solubility is directly proportional to absolute pressure. So the intent of showing this is that the best location to remove the air from the system is the topmost point, because that's the point where the absolute pressure is minimum. Now, we will start now discussing about few equipment. Obviously, the pump being the most critical. When you select a pump, you almost have seen a pump curve, which is something like this. So on the y-axis, there's the pressure, and on x-axis, there's the flow rate. So you would see a pump curve, like this. So pump curve is nothing but actually a map or locus of pump operation at various pressures, how the pump will behave. So as you can see, as the flow rate increases, the pressure developed by the pump reduces. I mean, if you see at this location, the flow was less, the pressure was more. If you increase the flow at this kind of point, the pressure reduces. So this is basically an operating envelope or operating map of operating locus of a pump. Now this pump curve is at particular speed. Let's say 50 hertz or 60 hertz if it is in UAE. I don't know what is the speed over there, but in India it is 50 hertz is is a synchronous speed. So this, if you run the pump at 50 hertz, you will get a operating envelope like this. If you reduce the pump speed, you would get a parallel curve like this, but it will again follow the same shape. So this is known as a pump curve. A system curve is nothing but how your system behaves. Now, for a system, for a fixed system, if you increase the flow rate, obviously the pressure drop is going to increase, correct? For pump, it is the opposite. For the system curve, it's opposite. If you go on increasing the flow, the resistance experienced by the system is going to increase. So at this flow, the resistance was, let's say, this. If you increase the flow, the resistance is going to increase. So that's how these two diverse kind of performance envelopes, we see. Now, obviously, we all know the pump system is going to operate where these two curves meet to each other, and that is known as operating point. So simple. So nothing great in this. You must have all seen this, for long years. Now, this all is good, in theory, that where the system curves intersect pump curve, that's the operating point, all look good, but that's not how it happens in real life systems. There are few variables which are actually introduced. Few of them I have tried to list. One is safety margins. When you calculate the pump head, invariably we go for some safety margins. Now, safety margins are not intentional, but let's say as as a safety, like for example, while doing the pump head calculation, you might not have exact data of, let's say, AHU coil pressure drop, or for example, a strainer or a chiller. In such cases, obviously, you would look for the submittals, of similar equipment and probably take 5% extra just to be safe. So nothing wrong with that, but then these things are introduced into the system. So first is safety margins. Then obviously, when you do the pump head calculation, you would select the pressure drop, when the equipments are dirty, right? But when the equipment is new, it offers very less pressure drop. The example is a voice trainer. So when you select the pressure drop in your pressure drop calculations, you would obviously select it in a kind of dirty condition. But when the systems are new, obviously the strainers and strainers are going to be clean. And imbalance by design, that's that's a reality of life. That some circuits will be very substantially long than others. This is something also which is unavoidable. So all due to this, what happens is you kind of selected by calculations etc. that the system would operate at this point. This was the flow rate and this was pressure drop, whatever. In reality, what would happen is the pressure drop will be less and you would kind of end up in over pumping. So this probably would be the actual operating point when the system is new, and then you would be forced to accept higher flow rate. So this is what actually happens in 99.999% of the systems. Is this clear? Okay. I think silence means
Yes,
it's clear.
Ajay, it's clear. It's
Yeah,
fine.
Yes,
we had
yes,
kept
yes.
others on mute. That's why all of a sudden
Okay,
nobody.
no problem.
No, no, it's
Thank you.
clear,
Thank you.
Ajay. Please go ahead.
Go ahead.
Yeah.
Go ahead.
Yeah. So this happens, then what should we do? Are there any ways to circumvent this issue and try to see whether this gap can be closed, or what best can be done? Because the bad thing about this is you are actually over pumping, uh, and while over pumping, obviously you might consume more power, imbalances in the system. So this is not really a good welcome situation. But at the same time, we know that this happens. So what to do? So let us try to decode a few things to address this issue. One of the things is first, pump selection. Can we kind of take care of this thing with pump selection? Now, one of the recommendations from AECOM is pump selected for closed chill water system shall have flat pressure characteristics. Now, what do you mean by flat? I mean, it's simple. It's a geometry. Flat is flat. Steep is this. So the recommendation for closed chill water systems, which is always the case, that we should try to select the flat curve. The intent of flat curve is the variation in head is not really appreciable with respect to the flow. Here, the your pressure gauge will keep on jumping. Here, you see the variation is not really much. So your pressure gauge is not really jumping that hard. That harsh. So the variation in flow, which is again a relative flight, because in system you are not going to get constant flow any which ways. Some walls are going to close, some some walls are going to open, few HUs are going to close. So variable flow is the relative flight. So that should not affect your pressures. So that's how the flat pressure curve is what is recommended by AECOM. Another thing is, you can see the pump curve starts from this point all way to here. So theoretically, you could select the operating point anywhere in between, right? I mean, if there is no other problem, I can select the pump or here, or here, or here, or here, anywhere. But then again, the recommendation of AECOM is don't select, really on very extreme right hand side, nor on the extreme left hand side. Now, extreme left hand side is known as a low cavitation or low flow cavitation, which is obviously very very clear that in these conditions the flows are less. So you could actually experience very high temperature, must say rise in the water. You could have cavitation, which may lead to your bearing losses. So this obviously is to be avoided. On the extreme right hand side, also you see a word in AECOM which is cavitation. So what do you mean by this cavitation? So this cavitation is due to excess flow. You can have actually lumps of flow. Lumping of the flow happens, and that can kind of damage your impeller. So this is the low flow cavitation. You could say this is the high flow cavitation, and this can have a lumps in flow. So what's really best point to select? So on this curve, there will be always a best efficiency point. AECOM says of that best efficiency point, you try to go plus 5% on x-axis, means in terms of flow, and minus 10%. So if you could select the pump in this region, that's the best practice as far as AECOM. Again, I'll repeat, there will be always a best efficiency point on a given curve, on a given speed. At the most, plus 5% on x-axis and minus 10% on x-axis. That's the best practice. If for some reason you can't do, they have also given a better practice, which is slightly more range, and a good practice which is again a much larger range. So if you really deduce this graph, you should not go right then plus 15% of BEP, best efficiency point, nor less than minus 30% of of the flow in best efficiency point. So if you could select the pump at this best practice or better practice or good practice at worst, you are kind of liable to get a good working of the pump. Anything beyond these ranges, you are actually endangering your pump in terms of its life. A little bit about parallel pumping. Now parallel pumping is again a reality of life. I mean, we never have a situation where we have only one chiller and one pump, and that feeds the whole system, correct? We always have standbys and multiple pumps. Uh, Now, this particular thing, parallel pumping, is especially important where you have 30, 40, 50 number of pumps in parallel. What really happens now, you just see what happens for a single pump scenario. When there are only two pumps, well, let's say there are two working pumps, each of 100 gallons per minute, and so the system requirement is 200 GPM. So I selected two working pumps of 100 GPM. So when both of them run, obviously no problem, they would produce 200 GPM. Now, if you switch off one pump and run only one pump, we think that the pump will give only 100 GPM. But that's not what happens. The running pump may give you 150, 160, depending upon the shape of its curve. So one running pump will give actually more than its rated capacity. Why it is problem? Usually, the power requirement of the pump is proportional to flow as well as pressure. But it's actually reliance on head is less as compared to flow when it comes to the power. So when one pump starts actually over pumping, you have all possibilities that actually it will consume much more more power. In which case there are possibilities that you may overload your starters. This obviously is a just example to tell you. This hardly happens when there are two or three pumps, but this can definitely happen when there are multiple pumps like 10, 15, 30, which happens in case of data centers. The simple reason is you would design the piping system or pipe size for all pumps running, and then associated say friction drop, etc., that you would consider. But when only one or two pumps are running, practically there is no resistance to the pump, and which actually forces the pump uh, to kind of overflow. So if you have a constant speed pumps in multiple numbers, this particular aspect has to be very very carefully thought. Arjun, Guru, yeah.
Yes, I have a question on this best efficiency point, BEP. So this for the selection software, if during the selection software, this is BEP has been identified by itself, or should we consider anything?
No, no, best efficiency point is actually by manufacturer that you and me won't know. So for a given pump, for a given impeller dimensions, given volute size, one curve of RPM will have one best efficiency point. So that is actually, I mean, if you see the pump selection curves, they identify the the BEP, the best efficiency point.
Okay, for this selection software, say example, it suggests some pump model, but it is having a deviation in this BP, like say example, minus the axis, you said the minus 10 percentage and 5 percentage on the positive
Hmm.
side of the x-axis. So if I'm considering this, suppose my selection is not sitting in this selection and you suggested best practice, better practice.
Correct.
So in this better practice, that life of the sail and the life of the impeller affects. So whether should we, as a engineers or a selection team, should we go for it or should we suggest the different model?
Yeah. Now I'll go back to, sorry, I'll go back to this. Yeah. You're talking about this. You're talking about, let's say, for a particular pump manufacturer, you don't get the selection, say within this, correct?
Yes, yes.
Yeah. So usually this doesn't happen. Now, this can happen, where, when you are actually operating point is, very skewed. For example, you have, very low flow and very high head. Something of that sort, if you have, then you may have, such kind of a situation that you are not going to get in this, best practice zone. Otherwise, for our air conditioning, system where we have decent flow and decent head, you really, don't have to, go out of, best practices. In booster pump application where when there is very low flow and very high head, there as per my experience, we sometimes don't get selection in this region, in which case you may go to better and good.
Okay.
Clear?
Okay, okay, clear, clear. And for the next slide, you are mentioning the parallel pumping. So the say example that project has been designed with three pumps, one duty in standby, like one standby. So in this case, say example, one more pump, like two pumps has been in duty with a VFD operation. Sometimes some logic has been implemented.
Yeah.
So what happens to the flow? Like whether it will be varying as per we will be achieving the design flow, or else are we compromising on the temperature, or are we compromising on this ed what you have mentioning?
Yeah. So I have not come up to VFD yet. This is all is still we are on a constant speed pumping. So issues, with this, how to solve that is, in the next, with VFD, how to solve that is, few next slides. This is assuming that all the pumps are at constant speed, multiple pumps. And if you kind of, switch off few pumps, then what happens? This is the problem.
No, okay, fine, fine. That's fine.
Okay. We have not yet come to the problem, how to solve this problem. Okay. Now, these are the problem statements only.
Okay.
Okay. Now, next is parallel pumping with dissimilar heads shall be avoided. I think this is quite logical that if you have a pump with, let's say, 6 bar and 3 bar, and if you kind of, try to run this in parallel, you have problem, right? The pressure by one pump, if it exceeds the shut-off head of other pump, the second pump will actually cease the flow. It won't operate, and it can cause irreversible damage to the pump. Now, the whatever problems we say always imbalance in flow, the head, and that's the reality. Now let us see how to kind of circumvent this to best of our ability. One of the answers is variable pumping systems. Now variable pumping systems can actually answer or solve this problem to a very, very great extent. But however, to apply this variable pumping system logics very, very correctly, we need to understand few fundamentals of variable pumping system. Again, I'll go back to my graph. This was a red is pump curve, let's say at full speed, and this blue line which you can see was a system line, correct? So a red line pump curve, blue line system curve, wherever they meet, that's a operating point. Simple. Now, if you resolve this system operating line into two components, one will be a variable loss. Variable loss means what? The friction loss or variable head loss, which is proportional to the flow. So this black color, so you resolve this vector or this blue color line into two components. One is a fixed head, other is a variable head. What is fixed head? We'll see later. Don't worry much about this at this point of time. Let us concentrate on variable head. So variable head is very simple to understand that if the flow increases, the variable head increases. Okay, it's actually again a parabola. Fixed head is what? Let us read. Pressure developed at design flow is equal to control head and variable losses in the system. So I have quietly used the word control head. 2 minutes back, I was using a word, which is fixed head or constant head. Suddenly I have changed to control head. So what is this control head? How do you control the speed of variable pumping? Is by a delta P sensor, correct? You would put a pressure differential sensor or delta P transmitter at, say further circuit somewhere. Some people put it in 2/3. Some people, put it in the most, important AHU. So what you are doing is there is the pump speed is basically controlled to maintain that delta P constant, right? So the differential pressure transmitter or DP transmitter decides the speed of the pump. Now that differential pressure transmitter setting or that set point is obviously in terms of pressure. It could be 1 bar, 2 bar, say depending upon the circuit and the loads. That DPT setting is also a pressure value. That is basically control head or constant. Why we call it as a constant? Whatever may be the speed of the pump, whatever may be the flow, you always want to maintain that delta P constant, right? The delta P setting, or delta P set point, you modulate the speed of the pump to maintain that value. In other words, that value is independent of the flow, independent of the independent of the speed of the pump. So it is constant throughout. So that's the reason why we call it as a control head, or DPT setting. So this blue curve is nothing but actually it can be resolved into two components. One is that fixed delta P setting, and other is variable loss. This is very important concept in next slides. Control head is pressure required to be maintained at design flow at location of differential pressure transmitter. So that value, 1 bar, 2 bar, or whatever, is this vertical axis distance, and this is basically a variable loss, which is actually function of your flow. Fixed part is not function of your flow; it's constant. Correct? Okay. Now imagine you are using a VFD. So this was the initial curve in the earlier slide. This was your system pressure. This was resolved into variable and control. So this was initially at flow Q1, which was your initial condition. This was your variable portion. This is your control head. Now let's imagine that the HUs have less load, few volts. Let me just give me 1 minute. There is some noise over here. Yeah. So from this initial condition, let's say there is evening, office is getting now emptied, say control wall starts closing. Now you really don't want Q1, you want Q2, less flow. You would imagine that, the pump will, straight away come to a speed, where it, matches the Q2, and that's the speed, right? That's what is our assumption, that initially the flow was Q1, a design flow. Now my flow is, my flow requirement is less, say 70%, 60%. So my speed will come down where it will intersect this line. My speed will get settled, and that's how. Here you will see this component, control head, has reduced over here, right? Now this is not allowed, because we just said this control head is basically independent of the flow. So if the pump is slowed down, flow will say reduce to Q2. Control head would also decrease. That you can see from the shape of the curve. Here it was this much, now it is this much. However, control system will not allow this to happen, because the main fundamental is that the control head will be always constant, irrespective of the flow. However, control system will not allow this to happen, as we always program the pump speed control based on to keep data P setting same. So what we feel logically should happen really is not making sense to the control system, correct? Because of the simple reason, the control rate is reducing, which should not happen. This can happen, this can reduce, no problem. This is a variable loss, is function of flow. It can say reduce, increase, no problem. The fixed loss cannot increase or decrease with respect to flow. So a problem now, what we feel logically should happen is not possible to happen, right? So what happens to the system? So what the control system does is actually it creates a new system curve. This was, let's say, your system curve, which started from 0. Now the control system somehow creates a curve which starts from some y abscissa, and then it continues like this. This is the control head. What it means is, even if the flow is less, no problem. The control head will be always constant. So if you see this distance, this is always constant. That's how a control system, devises a curve. It actually ignores, your system curve. It actually creates its own curve in the algorithm and thinks that the system will now has to operate like this. In this, you see all the problems are solved. There is always constant speed, constant control head, and variable speed, variable loss, of course, is a function of flow. So the control system creates a new curve, which is known as a control curve. Now, pumping system stabilizes and follows no system curve. It follows a control curve. So now the pump logic controller, or PLC, whatever you may like to call it, it actually follows this curve, which is known as a control curve. This is clear? Okay.
Yes, sir. You can proceed, sir. It's good.
Yeah. Now, how does it happens in real time? Now at part load conditions, we all know that the HU control valve, they will they would kind of try to switch reduce the flow through the coil. That there could be 10 HUs out of 6-7 HUs would kind of tune down their two-way valves, and that's how the flow in overall system would reduce. So again, to our curve, this was the initial curve. This was the fixed head. Now the flow has reduced. It has, let's say, gone to B to match our new Q2 requirement. A problem again, what has happened is the control head distance has increased. So if you expect the pump to go straight away to the left and settle out there, it won't happen. As this happens, point of intersection shifts toward the left with a rise in differential pressure across the transmitter. This would happen. Okay, when you start to close the valves, this particular thing would happen. But again, we all know the control system will try everything to bring back this differential pressure to set point value. So what it does finally, it does like this. This was our initial point. We thought it would go here, but it can't happen. Now what actually happens is, you remember the control curve, it will follow the control curve, and the final speed will be settled at a point where your flow is satisfied and this distance is equal to this distance. Where that happens, that's the final speed. Let me repeat again, carefully. The final speed is a speed where you are satisfying the reduced flow, let's say Q2, and this distance is equal to this distance. Whenever these two conditions are met, that's the final speed point. So above figure shows the result of control action and stabilization system at lower speed. This satisfied minimum control head requirement. This is kind of is achieved, and it is set to a reduced pressure drop at reduced flow and loading conditions. So this is a theory that when you say VFD reduces the speed to respond to the load, actually this happens at the background. So the final system curve, or the final speed, I should not call it as a system curve. Final speed is where you are satisfying your flow requirement, and the control head is honored. So that's how the control system selects the speed. Types of pumping system, I think this all there's no much need to spend time on this. In the primary secondary systems, you have a set of a production loop with usually constant flow pumps. You have a bypass or decoupler line. You have a set of secondary pumps which gets speed regulated with differential pressure transmitter, which is not shown here, but they're the same theory which we spoke about. In primary variable, obviously you don't have any two sets of pumps. It's only one speed of one set of pump who is responsible to pass the water from chiller to the last load. So this we all know. The speed variation of the pump in this as well as in this follows the same theory which I showed you in earlier slides, the pump speed modulation technique. Now, sorry, let me go back. You saw a primary variable valve here, which is also known as the minimum flow bypass valve. If you select this now, okay, all of us know that this valve is a valve which is it actually ensures the health of the chillers, correct? Because the chillers has a minimum flow requirement. I mean, you can't reduce the flow of a chiller to, let's say, 10%. There will be some minimum value, 40, 50, 60%. That has to be maintained through the chiller. That duty is done by this valve. So this is actually a very critical valve who actually ensures the safety of the system. Now, how to select this bypass valve or minimum flow bypass valve? What should be its diameter? I will first only read this. We'll go back again to that diagram. Bypass valve ensures minimum chiller flow through the operator. We all know, nothing great about this. At minimum system flow, differential pressure across bypass valve and index DP circuit is same. I'm sure this must be a bit difficult to understand. No problem. Let us read it again and then go back to the that chart. At minimum system flow, differential pressure across bypass valve and index DP circuit is same. I won't go ahead. I will again go back. What it says is when this the system flow is minimum. Let's say there were 10 chillers and now only one chiller is operating, that too at 40% chiller. Then really flow in this is very, very less, correct? It's very less. So you can also assume that the pressure drop in this line is also very, very less. This line and this line is very, very less. In other words, if I kind of extrapolate and say the pressure drop from here to here is zero, almost zero, then the pressure drop across this wall and this DP is same, correct? Because there is hardly any pressure drop in this line. At very, very low flow, you can say that the pressure drop in this line and this line is very, very low. So let us say it is zero. So the pressure drop across this wall, I mean the pressure drop or pressure differential across this bypass wall and your delta P setting is almost same. This theory is correct? Okay. So I'll go back again. Now it will make sense to you. At minimum system flow, differential pressure across bypass wall and index DP circuit is almost same owing to reduced pressure drop in the system. Now, hence, selected bypass valve shall provide minimum bypass flow at differential pressure equal to DP sensor setting in index circuit. Again, let us go back. Now, what is a minimum flow through this? So what it says is the pressure drop across this wall at minimum flow should be equal to your delta P setting. The minimum flow through this line is how much? The minimum flow say produced by the system, by the chillers, minus the minimum flow through the load. The remaining will be bypassed. Let's say a chiller system cannot go below 100 GPM. So 100 GPM, let's say, is minimum what you can get from this circuit. And at that time, my minimum load in the night wants only 60 GPM, for example. So chiller can give you no less than 100. Your requirement was 60. So remaining, 40 would go from here. So pressure drop across this wall at 40 GPM should be equal to delta P setting. Simple. This is the sentence. Selected bypass valve shall provide minimum bypass flow at differential pressure equal to DP setting at index circuit. If you could do that, in other words, you are saying you are actually selecting a valve with 100% authority. And authority is nothing but the ability to control the flow variations without, hunting too much. So minimum flow through this wall. What is it? You should select a wall. Let's say, for example, your differential pressure setting is 1 bar, and your minimum GPM, which minimum flow through this is, let's say, 60 GPM. So you should go to wall manufacturer and say, give me a wall with 40 GPM, and at 40 GPM it should have 1 bar pressure drop. If you could do that, then that's that wall is likely to give you a good smoother control. Mehul the Sunny. Yeah, please go ahead.
Hello, sir.
Yeah.
This theory is being understood, but this will be only applicable when the bypass wall is placed before any load. Am I correct?
Yes, that's correct.
Would this theory would be still applicable if the bypass is
Still
connected
applicable. Still
towards the
applicable.
end of the
Imagine,
load?
yeah, if this was here, say somewhere here, the same
Okay,
theory. The pressure drop to this is zero. The same thing. So this is a universal kind of I mean, irrespective of this is here or here or here. The theory is the pressure drop in this is at very very low flow is almost zero. So it holds good
okay.
for both the situations.
Got it, sir. Thank you.
Okay. So if you select, okay, I will again repeat, you should not select, bypass wall just abruptly, one cheddar flow, two cheddar flow. Find out, what is a minimum, flow that the system can generate. What is your, minimum requirement? Difference in that is a minimum flow through this bypass wall. And at that flow, the delta P or pressure drop of this wall should be equal to your delta P setting. If you could do this, then your wall is likely to give a very fine control. For primary variable systems, when many HUs shut off at same time, two-way walls also close very very fast. I mean, if let's say there are 100 HUs, and if you through BMS, if you shut them all at one time, then what will happen is their walls also say switch off at the same time. Now the flow immediately reduces. If the wall reduces, I mean, if the wall closes, the flow immediately reduces. But control system actually takes time to understand. There is always this system lag. So usually for primary variable system, you should not close all the HUs at same time. You should kind of have some schedule that out of 100 HUs, probably 25 HUs you can switch off now. Next 25 HUs probably 2 minutes later. Next 25 maybe after 5 minutes, so that the impact of flow reduction is kind of understood by the control system. It's not a sudden jerk. Next important after pump is expansion tank. Now, expansion tank is say required in closed water systems, chill water systems or hot water systems. We all know that. And what is the intent of expansion tank? It actually allows for expansion and contraction of water, because water changes its specific volume with respect to temperature. So if you don't have any system which kind of actually absorbs this volume expansions, you have problem. Expansion tank also provides a positive pressure to entire system, thereby maintaining say minimum pressure in the system above atmospheric pressure. This is very very critical. We will see later what it means. Okay, but for timing, just read and try to grasp this. Expansion tank provides positive pressure to entire hydraulic circuit, thereby maintaining minimum pressure in the system above atmospheric pressure. So we will see what does this mean. And expansion tank provides a point of reference pressure. This also we'll see what it means. So expansion tank is required for expansion and contraction of water. It also ensures positive pressure in the system at all points, and it also provides you what is known as a reference pressure. Let's say if you don't have expansion chamber and it is a completely closed system, then what happens? Now AECOM actually gives a beautiful equation. The relationship between pressure changes caused by temperature change. So if you kind of, take a pipe of, let's say, 1 inch pipe or 2 inch pipe, close it from, both ends and fill the water. So it's now enclosed pipe, and you change the temperature. Then what would happen is the temperature is changing, but there is no way for, water to expand. So what would happen is its pressure would increase. So this is the expression which talks about pressure changes caused by temperature. Now, don't worry much about this equation. The graph of this equation is plotted on the right hand side. So imagine the change in temperature is, let's say, 20 degree Fahrenheit, which is about 10 or 10, 11 degrees centigrade. So which can happen, let's say, if you have a chill water system, which is operating at 6, 7 degrees centigrade, and over Saturday, Sunday, let's say the system is closed, you can always expect that the chill water temperature could increase to ambient temperature. So in your region, obviously, it could be, say 40, 50, I don't know. But in India, it could be, 30, 35 degrees centigrade. So easily, 10, 12, 15 degrees centigrade rise is very, very possible. So here, obviously, I'm old timer, so I talk in terms of, degree Fahrenheit. So let us assume, the temperature has increased in that pipe at, from initial to say 20 degree Fahrenheit. If I consider a 1 inch pipe, this is the pipe. If you can see, the pressure rise is 600 psi. I mean, if you put all this thing in equation, for 1 inch diameter, 1 inch is what, 25, 26 mm diameter, correct? 20 degree Fahrenheit, say delta T is around 500, 600 psi. Now 600 psi, can somebody convert me in bar? Six hundred psi. 600 psi.
41.36.
41.
41 bar, correct? And do you think sewage, systems are designed for this kind of pressure? They are not, right? They are either at 16 bar, 20 bar, correct? If it is a small building, you are not going to design it for PN 40, PN 60, correct? You are going to design it for PN 20 or PN 10 or PN 16. So simple 1 inch line can have pressure increase up to 41 bar. So what it means is it will break, correct? Because it is not designed for that. Your walls, your heat exchangers, those are not designed for that 41 or that kind of pressure. Why that happens? Because water is not compressible. You can see for a simple 1 inch pipe with hardly say 20, this kind of 20 degree Fahrenheit rise, your pressure increase is becoming unmanageable. So that's how, and that's why the expansion tank in the system is very, very necessary. Okay, we were also talking about some, reference pressure. What does that mean? Again, these are the, two figures taken from, ISHRAE. You imagine when the pump is off, the expansion tank is, let's say, at the pump inlet. The pump is off. Obviously, you will see, what is the static head. Let's say 30 psi, 30 psi. Pump is not running, so pressure is same. Now you start the pump. You imagine that the pump head is 10 psi. So what would happen is the outlet pressure would increase to 40, from 30 to 40. The pressure here will be 30 only. This is very easy to understand. Let us take a very, very skewed example that for some reason you have put the expansion tank on the outlet of the pump. So when the pump is not running, obviously no problem. It's all static head, 30 meter head. When you start the pump and the pump head is 10, what would now happen is the pressure over here won't increase. It will be still 30 psi. What would happen is the suction pressure now would reduce to 20 psi to make up for that 20 psi head which is developed by the pump. So in any case, even the pump is running, the pump is not running, expansion tank is on the outlet, it is at the inlet. At given temperature, the pressure in expansion tank remains always constant, irrespective of the pump is running or not running. So that is why the expansion tank pressure is also known as a reference pressure. correct? At all other points, there'll be changes. Now here it will be 40. After some time, it will be 39. There'll be some drop. Blah 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 blah. Here it will be always constant. If the pump is running, not running, the expansion tank is at the bottom. After the pump, in between floor, terrace, basement, it doesn't matter. The pressure in expansion tank at that temperature. If the temperature is not changing, the expansion tank pressure will be always constant. That is why also it is known as a reference pressure as per AECOM. Now, what are the types of expansion tanks? This all we know 20, 30, 40 years back. We used to use open expansion tanks. Nowadays, obviously, nobody knows it. In between, there were air cushion type tanks where there was water and there was air and there was no surface as such. So these kind of tanks were there. I really don't know nowadays these tanks are available or not, because the last tank which I have seen was some 15, 16 years back. Now what much after that I didn't had seen such type of tanks. Most probably they are absolute. What is now used is a bladder type of tanks, which is basically inert gas like nitrogen over here and water from below. And this is a rubber kind of a gasket. So these are the tanks which are used, say nowadays. So we'll talk about only these tanks nowadays. Now we won't talk about these two tanks, in further slides. Obviously, expansion tank is a pressure vessel, and it is designed as per ASME Section 8 Division 1. In India, we use IS 2062 plates. I'm not sure what you use in Gulf regions, but these are MS kind of plates, say welded together. So this is how the tank say look like. It's a ASME pressure vessel. Now for sizing these tanks, you must have sized these tanks at some point of time in your project life cycle. You simply require a system volume, which is a total volume in pipes, in heat exchangers and bends and whatnot. So total system volume, lowest operating temperature. What is say lowest operating say temperature anticipated for that is, for chill water it is the operating temperature. If it is 6-7 degrees centigrade, then that is the lowest operating temperature. Highest operating temperature can be, if that system is, let's say, closed for a few days, then the water temperature can increase, and at worst it can go to ambient temperature. So highest operating temperature could be the ambient temperature. A minimum pressure in the tank and a maximum pressure in the tank. This we will see in few slides. So these are the 5 parameters which are actually used to size any expansion tank. So this upper 3 are say clear. System volume, lowest temperature, highest temperature. These 2 we are not yet talked about. We will talk about this subsequent slides. For this is AECOM formula for diaphragm tanks, which looks something like this, where VT is a expansion tank volume, VS is volume of water in the system. Then there are, don't worry much about this formula. We are going to see this later how it comes. Then this V2 or mu2, whatever you may like to call it. These are basically specific volumes. P1, P2 are minimum pressure, maximum pressure, which we are yet to see. And this is a term which is for steel expansion. So this kind of formula is given in AECOM. Don't worry much about the formula. Let us see now. We have not talked about yet pressures in the tank. So what are those? Lower pressure is selected to hold 10 psig pressure at highest point in the system. Now, highest point in the system, let's say it's a tall building and 20-30 story building. The plant room is in the basement. Then obviously the lowest pressure and the lowest, the lowest pressure will be at the highest point. Now that highest point should also have 10 psig plus pressure over the atmospheric. So if you don't have any positive pressure, the pressure at the highest point is actually equal to atmospheric, correct? I mean, there is the, say at the topmost point, the pressure is usually atmospheric pressure, but we want plus 10. So the lowest pressure in the system should be 10 psig above atmospheric pressure. So that's the lowest pressure. Highest pressure or higher pressure is obviously if you select PN16 as pressure rating, you obviously don't want the system pressures to go say beyond PN16. So in that case, PN16 is a higher pressure. So and these two pressures are in the expansion tank. So lower pressure in the expansion tank is such that the pressure at highest point is 10 psig. So 10 psig is not pressure in the expansion tank. Is the lowest pressure in the expansion tank should be such that the lowest pressure in the system is 10 psig. Now how that we'll see later. So just you keep in mind that the minimum pressure in expansion tank should be such that the minimum system pressure should be 10 psig of atmosphere. And obviously the highest pressure in the expansion tank shall be such that maximum pressure in the system should not be more than its rating, PN10, PN16 or whatever. So that's how this equation is to be used. Now, the best way to understand this equation is to see whether we can find out whether this equation is right or wrong. In other words, if we try to mathematically derive this equation, we will understand it more. So this is attempt to derive that equation. These two are expansion tanks. This is when the chill water system is running. Let's say it's your commercial building. So 6 to 7 degrees centigrade is usual, your chill water system. For data center, it could be high. So when system is operational, the temperature is, let's say, 6 degrees centigrade. So, and when this system is off, let's say weekends, the chill water temperature rises. And as we spoke, in worst case, it will rise to ambient temperature. So this is operational system, and this is when the chiller system is shut off. P1 was the pressure when the system was running. When the system was switched off, actually the water will push this surface up, correct? So this was air volume or nitrogen volume. When the temperature of the system increases, or when the chiller system shuts off, I should have actually drawn this line slightly up so that this VL2 would have been less. This is my drafting error, but you should understand that VL1 was the volume in the tank when the system was running. When the system was switched off, the temperature of the water increases, and this bladder was actually pushed little up. So VL2 was less than VL1 since the bladder has been pushed. At that time, let's say the pressure was P2. Simple, let's don't worry much about what is P1, P2. When the chill water temperature was 6 degrees centigrade, my air volume was VL1, pressure was P1. When my temperature increased, my bladder was pushed. I got now this VL2 volume, the pressure was P2. So VL1 is volume available in the tank at pressure P1 at lower temperature, and VL2 volume available in the tank at pressure P2 and at higher temperature. Again, a spelling, wrong thing here, at higher temperature. So also now let us see that rho 1 be specific volume of water at lower temperature. I mean at this condition at 6 degrees centigrade or 7 degree or whatever is your so operating temperature. Let's say rho 1 be specific volume of water at lower temperature. Ameya Kamli, some line work is going on. Okay. So let say rho 1 be specific volume of water at lower temperature, and rho 2 be specific volume of water at higher temperature. Is this clear? This slide?
Yes, sir. Good
Okay.
to go.
I think Ameya, you are doing some line work. I don't know. Can this be removed? Yeah, thanks. Arjun Guru has raised his hand.
Yes, before proceeding to next slide, just want a clarification on this, right? So you said based on the unit chilled water off and on conditions, this volume will be varying and the
Yes,
pressure in the tank will be varying.
correct.
And when we go through the previous slides, you mentioned that the expansional before the pump and after the pump, it will be
Hmm.
the constant. So
Yes.
how we can make this justification like
Yeah.
that
The
slide
word
and this slide?
the word I used was the pressure in the expansion tank is constant when the temperature is constant.
Okay, in the previous
Okay.
slide, correct?
Yes. Yes. So it is at constant temperature, the pressure remains same. Now,
Okay,
when
okay,
the
fine,
water
fine.
temperature changes,
Got
uh,
it. Okay.
water expands and the pressure changes. So this slide clear because this is going to now be kind of referred in few next slides. Okay. So again, at the last point, rho 1 be specific volume of water at lower temperature and rho 2 be specific volume of water at higher temperature. So specific volume is nothing but inverse of density in a way. Now, mass of water at lower temperature is basically Vc was the system volume and specific volume at lower temperature. So mass of water was this much. Now mass of water at higher temperature is now what Vc. We just saw that there is some expansion of water. So let us call it as a delta or a triangle. So now this is a system volume and specific volume at higher temperature was rho 2. So mass of water at lower temperature was this. Mass of water at higher temperature of this. Now, though the system volume have changed, the mass of water has not hasn't changed. Correct? We have not kind of released any water from the system. So mass of water when the system was running and the system is off is going to be same. So in other words, these two terms can be equated to each other. Right? Since mass of the water at lower and higher temperature is same. So you can actually always equate these two terms. So Vc is a system volume, rho 1 is at lower temperature, delta or triangle, whatever you want to call it, is a expanded volume, and rho 2 is at higher temperature. So you can always equate these two equations. Vc upon rho 1 is equal to Vc plus triangle upon rho 2. So these two equations are equated, which is a fair thing to do. And with some mathematical manipulation, I separate out this poor triangle out. Okay. So expanded volume, I have kind of expressed in terms of, system volume and ratio of specific volumes. So this is the expanded volume and I call this as equation 1, right? All valid, no mathematical, say deviation, since the mass of, water will be always same. We are assuming that there is no seepage of water. So we got the first equation for expanded water volume in terms of these two terms, water volume and ratio of specific volumes. Let us call this as equation 1. Now, the air or nitrogen in the tank bladder, okay, uh, you can actually apply Boyle's law. Boyle's law can be applied only when there is a isothermal conditions, theoretically. But here we are saying the chill water temperature is changing from 7 to 30. However, for the air, you can actually assume the temperature rise to be minimal because, air and water are separated by actually a bladder, which is a thick, rubber bladder. So, with say reasonable in, say accuracy, you can, always say that the air or nitrogen in the system has not undergone much change in temperature. So for such system, you can always apply Boyle's law. And what Boyle's law says, PV is equal to P1 V1 is equal to P2 V2. So I can always apply P1 VL1, the earlier volume and the earlier pressure, and increase pressure and reduce volume. So this is the Boyle's law. So which with very less error, I can actually apply this law to the system. So again, some mathematical manipulations, P1 upon P2, I separate it out, is equal to VL upon V2. I subtract one. I subtract, these two terms from one from both sides, which is still a valid mathematical operation. So 1 minus this and 1 minus this is still, a valid mathematical operation. I again do some more changes and VL1 minus VL2. Now VL1 minus VL2 is nothing but again the expanded volume, right? So I again try to separate out this triangle and arrive at this equation, which is now a tank volume and ratio of the pressures. I got this equation of expanded volume in terms of ratio of the pressures. I call this as equation 2. You remember equation 1 was also for triangle, equation 2 is also for triangle. So I can very validly equate those things. We see upon this, I mean this I can always equate. I can do some again mathematical jugglery. VL1 I can took as a tank volume, the remaining terms on this side. So the tank volume is basically VC is system volume, rho1 upon rho2 minus 1 upon P2. So this is the equation for tank volume. Now here we didn't consider any steel expansion. We just talked about only water expansion. So because what happens is when temperature changes, piping also expands or contracts, and when piping expands, it actually helps to accommodate some of the water. So this is the term which is we will take from ISHRAE, that is if expansion of steel piping is to be considered, you need to subtract that expansion, correct? So this. So now you see this equation was, I will go back, was same as that we saw here, except this term, because for the derivation we didn't actually worried much about the piping. So if you neglect this term, this side of the equation is exactly same as we could derive it. Yeah, here. And this term is added to actually take advantage of steel expansion volume also, so that you can actually optimize your tank size, where alpha is linear coefficient of steel. If it is copper, it is different. For aluminum, it is different. And this delta T is basically the temperature difference between ambient and desired chill water temperature. So that's how we could see that the equation in ISHRAE looks to be good and logical. Any doubts in this? Good. Now, we actually very halfly talked about 10 psig and PN16 and tank pressures. So this slide should make it clear. P1 and P2, whenever we talk, are the pressures in the expansion tank. Now let us consider an example where your chillers and pumps were in the basement, your expansion tank was on the terrace. So this was the situation, and H was the height of the building or the hydraulic circuit. So in this case, I need to find out minimum pressure and maximum pressure in the system. So the minimum pressure should be in the system. So okay, minimum pressure in the system should be 10 psig above atmospheric. So minimum pressure will be always at the topmost point, correct? So my expansion tank is also on the topmost point. So minimum pressure in the expansion tank is also 10 psig. 10 psig is all over here is good. So my expansion tank minimum pressure was also 10 psig. Maximum pressure is what? Now the maximum pressure will happen over somewhere here, right? After the pump. Now let's say PN16, or say your relief valve setting pressure. So that was here. But I am concerned about the maximum pressure in the expansion tank. So what should be that? So it should be this pressure, let's say PN16 minus H, correct? Because that is the reduction. This is the static head, which has gone into the system. If I put the pressure goes over here, I will see the pressure at this point minus the static head. So maximum pressure in the expansion tank can be PN16 or PN10 minus height plus say friction loss from A to B, because the pressure over here should be sufficient to take care of this friction drop, correct? So my maximum pressure in the tank can be PN16 minus H plus pressure drop from this to this. So with this, I will call this as a P1, I will call this as a P2, I'll put these values in that equation, and I will use these values. Now it can happen that the expansion tank can be in the basement itself. It can happen. So now what is minimum pressure in the tank? I know that I want 10 psig minimum pressure at the highest point. So 10 psig is here plus H. Now in expansion tank, there's a 10 plus this H and minus friction. This, for time being, you can keep aside. So in the expansion tank, the minimum pressure in this location can be H, the static height, plus 10 psig. This is the minimum pressure I should have. And maximum pressure, you can assume, same pressure over here, that is a relief wall pressure. So PN16. So this is how the P1 and P2 are selected. They are, strong function of where the tank is located. Is this clear? Yeah, Arjun, Guru.
Correct me if I'm wrong. That for the first diagram, the pressure, minimum pressure, it's saying as 10 psi. Plus, we have to add atmospheric pressure, right? 10 psi plus atmospheric pressure.
Yes. Yes, that you should do in all cases. That, I have not written here, but that's in addition to all. It's absolute
Okay,
pressure.
done.
Yeah. I've just talked about it. See, this is important to understand that 10 psig is not pressure in the expansion tank. It's at the minimum, at the minimum pressure point. So if your tank happens to be at that point, then it's 10 psig. But if your point is at, somewhere down the line, 10 psig plus the static head, that's the minimum pressure in the tank. So that's how the values of P1 and P2 are say decided and used. I will really run fast because a low delta T syndrome can itself be a 2 hours lecture. So I will just try to do introduction. Many of you might know this. So low delta T syndrome is a phenomenon which occurs in almost every chill water system. At what it means is at partial load, often or most of the time, system fails to maintain the design delta T. And low design delta T puts power penalty and low, and the chiller water pumping also increases. So basically, low delta T syndrome has two ill effects. It actually forces you to over pump, and so over pumping is obviously excess power spending on the pumping system. And due to overpumping, you need to fire the chillers to satisfy the flow and not to satisfy the load. So this is the problem. Ideally, the chiller should on and off based on only load. But if it is to respond to flow, to start or stop, that is something which is a major inefficiency. So we'll talk about that in next slide. So low delta T syndrome is overpumping and also the chiller power. Now, what is effect on chiller? Why we say that, we understand that, due to low delta T, over pumping is happening. So pumping power is wasted. That is understood. But what about chiller? So just see what happens. Now, you imagine a chiller with, a commercial, building application, a regular 7-degree supply and 12 degrees centigrade heater. So if you want this, probably the manufacturer needs to boil the refrigerant at 6 degrees centigrade. SST is saturated suction temperature. So to give you 7 degrees still water temperature, the manufacturer will boil the refrigerant, maybe R134A or whatever, at 6 degrees centigrade. So there is an approach of 1 degree centigrade, correct? Nowadays, obviously, there are evaporators available at much lower approach than this also. But for this example, let us see, say assume that the refrigerant is boiling at 6 degrees centigrade. So the manufacturer has selected the heat exchanger for LMTD of 2.8. So LMTD is nothing but, if you put T1, 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 this 7, 12 and blah, blah, blah into this equation, the log mean temperature difference for this condition for that evaporator is 2.8. So, the heat exchanger performance is, is not arithmetic actually. It's logarithmic always. So you don't, do average of this. It's actually in a logarithmic way. So the manufacturer will, give you heat exchanger, which is with LMTD of 2.8. Okay, all done. So you got the chiller selection and you operated chiller at site. Now, instead of 12 degree return, you are having only 9 degrees. So delta T has, reduced from 5 to 2 degrees centigrade, right? So this is the low delta T syndrome. So your written water temperature is 9, and so instead of 12, it is 9. Now to maintain the same LMTD, because the heat exchanger, designer has designed the heat exchanger for you. So now for written water temperature of 9, and to give you 7 chill water temperature with LMTD of 2.8, you need to boil the refrigerant now at 5 degrees centigrade. Okay. For 5 degrees centigrade delta T, you used to boil it at 6 degrees centigrade. But for now 2 degrees centigrade delta T, from 9 to 7, you now need to boil it at 5 degrees centigrade. So which means your compressor is doing now more lift. Earlier it used to suck the gas from 6 degrees centigrade to condensing temperature. Now it needs to slightly go down, pick the gas at 5 degrees centigrade and push it up. So the reduction in delta T is reduction in SST. This is increases the pressure ratio, and that's how the chiller efficiency gets affected. Is this clear? The intent is not really to explain you the full low delta T syndrome, but it's just introduction. So two critical parameters: over pumping, so wastage in pumping energy, as well as chiller energy. So low delta T syndrome is a problem always. This is one slide which probably is not applicable for your region, but good to know kind of thing. Freezing assessment. The places where, say in Eastern Europe or Northern Europe, where the chill water or condensed water systems are in a place where the temperature can go sub-zero, -10, -20, -30. If you really don't give attention to anti-freezing systems, you can really have a problem that your pipe can burst. What happens is when the water becomes ice, actually its volume increases, and the pipe or system can burst. So how do we do the freezing assessment? So again, there is a formula in AECOM. Don't worry much about this formula. What it does, it shows you the time to freeze. Based on your diameter, your inside diameter, the chill water temperature or hot water temperature, and what is the ambient temperature. So this is a formula in AECOM. This is an example for a 300 mm pipe. What is important to know is these two. This formula will give you the freezing time. So for this given set of conditions, this particular 300 mm or 310 mm pipe will take 9.2 hours to freeze. Okay. Now, based on the AECOM weather bin data, you just see for how many hours continuously the temperature was below 0 degrees centigrade. Now, in this particular case, the minimum ambient temperature, below 0 degrees centigrade, was for 9 hours continuously. This pipe takes 9.2 hours to freeze. Of course, this is too close conditions. Too close to be too comfort. So we provided an insulation to this. But let's say this figure was only 2 hours. That for only 2 consecutive hours, the water the air temperature or ambient temperature goes below say 0 degrees centigrade. Then I would not have too much worry, okay, about the condition, because I want 9.2 hours to freeze it, whereas the ambient temperature will be sub-zero only for 2 hours. So probably I may not think to give a insulation, or I may give a very shallow insulation. So this is how the analysis is done. If this is a reverse condition, then let's say this was 9 and this was, let's say 20 hours. So now you need to go on increasing the insulation thickness to kind of make you comfortable in this. As I said, this is always required to do only in conditions where there is sub-zero temperatures. Otherwise, in India or probably in your region also, I don't know, it may not be required. Clear? And I think that was my last slide. Thank you. Stop sharing.
Thank you,
Yeah.
Ajay.
Questions?
Amazing.
Amazing, really amazing. I think we can open for the question and answers for 5 minutes. Any questions, please unmute your mics and you can ask the question.
Yeah.
Mr. Ajay, the questions which I had shared with you, I hope you have covered everything. Anything specific you would like to answer from that list also separately,
Yeah.
you can
Yes,
take up now.
let me open that list. Just give me a
Yeah.
minute. Okay. Yeah, I think there are a few questions, which are not related to this topic, cold room and etc. etc. So I would kind of, take relevant questions only for, yeah, please explain psychrometric chart, not relevant for this. Low delta T syndrome, we talked about. Maglev technology. Is maglev technology available in air-cooled chillers? Yes, though it is not, applicable to this topic. Somebody has asked a question, is maglev technology applicable for air-cooled chillers? Yes, it is applicable. I mean, we have seen, air-cooled maglev chillers as well. Discuss regarding, okay, district cooling. Somebody has asked, what is the difference between district cooling and chill water system? So in fact, you all should know better than me because, your region has, many district cooling plants. So it is actually the same. There are two, three differences that, district cooling plant is actually, self-service. Like, you have, say electricity, that's how, you can actually purchase chill water. So a few advantages in chill, in district cooling is you can actually have advantage of, a diversity. You can have actually a smaller size plant as compared to, if you have 10 buildings and if you want to have 10 different, buildings, individual plant, as compared to, let's say, if you have a district cooling plant, your installed tonnage would come down due to diversity. This is, one of the, say advantage. And as a client of the building, you don't have to upfront invest. So your initial capital cost also is less, which kind of, you can bring about by, paying the chill water as and when you install. I think as a engineering, the systems are same, but a few, advantage of district cooling are basically you don't have to upfront invest and the installed tonnage can be less. Otherwise, how to select pipe based on the chill water flow? This, uh, pipe size everybody can do, right? I don't know who has asked this. How to select pipe size based on chill water flow? So in my this thing, I used to charts, but nowadays I think many softwares are available now, where you could input the flow and the pipe size comes out. Psychrometry, chiller water plant. I think these were the questions which were related to today's topic.
Mr. Ajay, in the chat box, there are some questions posted.
Yeah.
If you want, I can read it. What pumping system is best if we have a chilled water plant with following combination of chillers and multi-purpose heat pumps? Air-cooled chiller with total heat recovery, 2 numbers. Air-cooled chiller with partial heat recovery, 2 numbers. And multi-purpose air to water heat pump, 4 pipe unit, 2 numbers. This is from
Okay.
Usman.
Okay. So what pumping system is best if we have chill water plant with following combination of chillers? Okay, so it's basically, variety of chillers, air-cooled chillers with partial heat recovery. Now, uh, uh, see, primary variable system, we were talking about, this low delta T syndrome. Now, one of the, ways to circumvent this low delta T syndrome is basically use a primary variable because, you can actually, vary the flow, with respect to load. So if you go with primary secondary, obviously you lose control over delta T from 99% load itself. So the primary variable system are actually best for this low delta T syndrome kind of thing. But if varied things are there, I mean, as I understand from this is they have probably 100-ton chiller and then the same 1,000-ton chillers or different type of chillers. What we have been doing in recent times is primary variable, secondary variable. So this actually takes care of your variability in primary size plant and secondary is basically again as it was. So primary variable, secondary variable, these are systems now are getting quite popular now. So I would have done this primary variable, secondary variable, because if I do constant primary, the problem is it's a very simple system, simple to operate, but low delta T syndrome actually will kill your electricity bills.
Next question is, which type of pump is more efficient, whether horizontal end suction or vertical?
Okay, now pump efficiency is actually function of the operating points also. At certain flow and head conditions, certain types of pumps are efficient. At others, different pump conditions, the others are different. So I will not be able to tell that horizontal just say is only efficient. ऐसा नहीं है. I mean there is a gamut. I mean there is a locus of a certain head and flow for which certain type of pumps will be more efficient. The only thing is, if I just wanted to talk one thing which I didn't include in my presentation about if you have a very high static head. I mean, if there's a very tall building, you should actually try to have pump with with what I should say, the water entries from both sides, split casing pumps. If you consider vertical online with only from one side the water comes, then there are imbalance forces. For if it is a very tall building, then those forces can be very detrimental, and that can damage the impeller. So for very high rise building, it's always good to have split casing pump in which the water comes into the eye of impeller from both the sides. So that's how this vertical pressure components get nullified. I hope you got my point. You know what I'm trying to say.
Yes, sir. So the next question is, what would be the probable causes of reverse flow problems?
I really don't know what is it, reverse flow problem. I never faced it. What is actually a reverse flow?
Mr. Amar Singh, can you clarify if you're there? Mr. Chauhan, Amar Singh Chauhan.
Hello. Yeah, I'm audible.
Yeah.
Yeah, sir. Actually, when the particularly at the lower loads, partial loads, that secondary pumps, there is a problem with incoming and outgoing the reverse flow pump flows reversely. That was.
Reverse.
Yeah.
Can you a bit explain, because it's hard for me to understand. Means you are saying the pump is running, but the water is flowing in opposite direction.
Yes, particularly on the district cooling, and there was a VFD, and there was certain areas due to the like imbalance into the flows. Yeah.
Oh, sorry, I have not seen actually, so I'm not able to answer this. I mean, reverse flow is something which you are saying the pump is running and the flow is opposite. So sorry, I have not seen the situation like this. So probably I may not be
So
able to answer.
maybe the reverse return system may be talking, I think.
No, reverse return is simple. He's saying reverse flow. So whatever that means, but the reverse return is of course it's simple. It's your piping design. But sorry, I think either I have not understood the question, or probably you are not able to explain it.
Sir, if you allow me, this can be only the cause of this could be the wrong set point of the delta P.
Hmm. Hmm.
That could be the only cause which I could think of.
Okay. Okay, possible. But frankly, I have not seen this, so it's not right for me to comment on that.
I mean, as long as the pump is working, there cannot be a reverse flow.
Exactly. That's what I thought too.
Okay, next question, sir, is what are the key design considerations when choosing between an open and closed chilled water system?
Okay, a simple open chilled water systems are mainly for now industrial applications where there's a hot well and cold well. Where you want actually where the load fluctuations are very great. In industrial process applications, uh, the chill water is, used to cool the processes, or it is, used to cool the process where the temperature, variations can be, very, very sudden. So what they do is they have, what is called as a, hot mixing tank and cool tank. So this is an open system. But for, our type of systems, it's always closed. So to answer the question, the industrial systems, which is very with rapid load variations, which really you don't want them to, affect towards, chill water temperatures, very rapidly. There only the open systems are used.
The next question, sir, is for modern construction. Currently, two-way walls, VFDs are very common, also VAV, to reduce the energy consumptions. But in your knowledge, is there any other new strategies to reduce energy consumptions?
For the same question for modern, it's one so reduce energy. In other new strategy to reduce energy consumption. Okay, now see VFDs or two-way walls and all that, is okay. This has been done for many years. So this is not really a new thing to do. When you talk about energy reduction, it has to start from the design. I mean, let's say I am designing application, say office application, for example. I straight away do the heat load calculations and blah 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 and select the chiller at 6 degrees centigrade. Now, if I could spend some time and kind of analyze if instead of 6 degree, can I select a chiller at say 7 degrees centigrade? Can my all in say inside conditions are okay? Uh, if it's okay, can I see 8 degrees centigrade? So that's the way to do energy efficiency. Energy efficiency is not really to use energy efficient equipment. That's one part of it. The other thing is, I mean, the main thing is by design, can I do something? The heat load calculations. I mean, do I have not kind of, say oversized the things? Have I taken, proper storage factors, etc.? So is my load optimum? Once that is optimum, is my chill water temperatures, is that, the best thing? Why only 6? Why not 7? Why not 8? That is done then, chill water delta T. I select delta T of 10, but is it okay if I go with 12? So such kind of, analysis, that is actually the key for energy efficiency. So efficient pumps and efficient, VFDs, that's one thing. But I think, the sustainable design starts with, your drawing board.
Noted, sir. The next question is what water treatment methods are recommended for each system and how do they differ
Yeah.
in a
So,
sustainable point of view?
okay, so water treatment is actually not, really my, great subject. I have, few things to tell you. Uh, in chill water, being it's a, closed water system, the earlier chemicals, say using sodium nitrate, etc., they have been used for ages, no doubt about it. But there are nowadays, good systems. They use actually, non-chemical systems, which is, magnetic, and then, ion-based systems, so that the chemicals, in the system, they don't actually affect the life of the components. So, say magnetic type of things, where all that, dirt, etc., is kind of ionized or, magnetized and then, easily removed.
Noted, sir. I think from the chat, we have taken all the questions. Any other questions, please ask now. If not, I have a request. Those who have not registered but joined the link, please post your email ID and full name in the chat box immediately because we don't have your data to issue certificate otherwise, participation. So please in the chat box, put your email ID and clear name, what you want on the certificate, yeah? Coming to Mr. Ajay now. Mr. Ajay, it was really amazing. Means words are not enough, to be honest with you. It was really amazing presentation, technical. And for UAE chapter, it is one of the most technical we had in last 1 year because we are just evolving as a sub-chapter. So of course, India ISHRAE is like more than 4 decades old. So we hope we reach those levels very soon with support from people like you. So it was really amazing what we got from you today. Mr. Ajit, if you're there, thank you note from your side also will help.
Thank you. So, good opportunity. So thanks for giving this opportunity. And if you want any other lectures on low delta T, probably I can also ask few say experts to get connected, because that's also a very important chapter, low delta T.
So this is exactly what we want to know about low delta T and the efficiencies at low delta T.
Absolutely.
Sure, sir. We'll organize second training very soon. We'll bother you then for sure. That is, thank you so much, sir. Really appreciate your time.
Thank you.
And any other questions, please post it in the chat. We'll send it to Mr. Ajay and get the replies to you. Any feedback, sir, you would like to give us as a ISHRAE UAE chapter also? You're most welcome for any improvements from
I
the
am
training.
also the Mumbai chapter committee member. I am planning co-chair, so I have that dual hat also. My again request to all is whoever is not ISHRAE member, please become one. I mean, this is just for example. There are many more say experienced people like me, much better than me also, who can actually give such lectures, and that's actually a value addition of ISHRAE. So I recommend everyone to take the membership.
Thank you, Mr. Ajay. It was really nice of you to say that. Thank you, all the participants. Really appreciate. I will keep the chat box open and the link open for those who are putting their email ID and names here. Thank you, Mr. Ajay. Really appreciate
Thank
once
you.
again.
Thank you. Bye.
Thank you. Bye. So the chat is open. Please let your name and email ID keep coming in.